first of all, a term as a way to approximate function with polynomial. So the RA extent is like this. So maybe the function itself is like quite messy, something like this. So originally, maybe in high school, we try to like maybe approximate the neighborhood of this point, the function value as some straight line. Right. That's in high school. So you may write out something like f of x plus h is about f of x plus h f prime of x. Correct? And you might know that, observe that h equals to f of x plus h f prime of c is by MVP. So it seems like these two are not differ like that much. All right. So that may be the one of the incentive that why we consider that like approximation. But we not only want to care about like this line, we want that to be like accurate. So how can we do that? The way that we make it more accurate is to add some higher order terms on the approximators. So it would be like to write down something like, so the goal is to write down something like f of x plus h equals to f of x plus let's say a1 f prime of x plus a2 f prime of x. All right, that's our goal. Approximate. All right, I want that approximation to be more accurate. So write down something like this. Then how we do this? How we do this? We want to approximate things in polynomial. So maybe we start with polynomials. Right. Let's say maybe s squared. S squared. And we let f of x equals to x squared, and with that x plus x0 equals to 0. Right. So I want to write out something like h squared equals to f of x. F of x is f of x0 plus a1 f prime of x0, and a1 of h, a1 of h, a2 of h, a1 of h, a1 of h, f prime of 0 plus a2 of h s 0 plus n h n x0, something like this. Right. And what's this? This one is 0, like this. This one is also 0. Right. Gives you if you differentiate it at 0, then you got 0. And thus, 2a to h thus 0. So it seems like a to h should be this one. You can change that to xn, and you will see that a and h should be defined as right? They're just from this kind of thing. You know, you want something like this. So back our term, if f n minus 1 comma t, a, b, and f n exists on a, b, then we want f of x. I write two versions. F x plus h. It should be approximately f of x plus h f prime of x. F prime of x and minus 1 f n minus 1 x. And what do I mean by this approximate? I mean by this. You should observe that this kind of MVT, right? From this. We should observe that this kind of MVT. So try to find this C. So the remainder term here should be like similar to that one. Should be like this. That's the version from this. But I think the one you have was accordingly. It's f of x equals to f of a plus sum over I from 1 to n minus 1 x minus a to the I f I x this x minus a to n f x. Sorry, should be a. I think that's the version you have learned. And you can see that these two are the same. I just change x to x plus h and x minus a to h. And how to prove this? You have, I think I have learned one proof on video, but I'm going to show another proof. And I think this proof is like, will make you to learn like the importance of generalized MBT. Right. I think he used some general rules there. If you remember, it used some like 0, 0, and there's some points, or there is some point, something like this. So I did this like more directly. So now you're thinking about, you want something like this appears, and you want like something like this appears, and you know that why this term will appear. Why this term would appear? Because you differentiate this one n times. Right? Why this one appears? Because you differentiate this term. So you have two things to differentiate. One is f. You need to differentiate this, and you need to differentiate this. So you want to differentiate two terms at the same time. A way to do this is,
wait, but where's the h to the powers?
Yep, you're right. S squared. H minus 1. H. Yes. So you want to differentiate this term, you want to differentiate that. So what do you do? A way to do that is use generalized MBT. So you can handle both differentiation at the same time. F of x equals to f of x minus f of a plus sum over I. This one of I x x minus a I. And as I said, I want to differentiate this term. So g of x equals to x minus a to n. Right, so we got this. F of x minus f of a. This one's clearly 0. So g of x minus g of a. So sorry, first observation that is, it's not hard to see that f, not hard to see that or to see f of a equals to f prime of a equals to f n minus 1 a equals to 0. And so g of a blah 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 equals to 0. Alright. So this one. It equals f of x, g of x. Right. But on the other hand, it also equals f prime of c1, g prime of c1. Right? And it equals what? It equals f prime of c1 minus f prime of a. G prime of c1 minus g prime of a. And again, these two are 0. So by generalized MBT, you know this one equals to f prime from c2, g G prime prime C2. And again, these two are 0. F prime prime C2 minus F prime prime A. G prime prime C2 minus G prime prime A. Alright, so equals, it equals Fn of Cn, Gn of Cn. Right? What's this? This is this, and this one is F and Cn.
Wait, so first one, so is the last x a on the first one?
Yep. You know this one. Are you gonna call this? This one is f of x was the downside x to be x minus a to n. Alright, so just move it here and done. That's the alternative proof of Taylor's theorem. I think that's more straightforward to me, but I'm not so sure if it's more straightforward to you. Why this one is more straightforward to me is because at this point, I see I need to handle two differentiation. So a straightforward way for me to like handle that things at the same time is to use generalized MBT. Yep. But if you like go on to the math department's introductory to the introduction to analysis course afterwards, and you will learn about integrals. I think the integral is like the most direct way to see Taylor's theorem, but because you haven't approached that yet, so I'll skip that. MBT, so it's
Yeah, so
it's like A x and C1 here, C2 here, Cn here.
yeah, so it's only the open interval between.
Yeah.
Or closed.
Open. So you need to write down something like for some C in x a, something like this, or between x a, for some C between x a, because you don't know which is bigger. And why is between? You can see that from here. Just keep using MBT. So of course everything is between x and a. Okay, the limit of functions. Limit of functions. Check what should I cover. Is that one easy for you? I don't know what to review about this one. So it's only about definition, you know, point wise. You know, like, whose wise convergence. You know, something like immediate form, convergence. As long as you know these two. Oh, okay. Also a theorem that C1 A B. Do I need C1? No. So 0. Okay, that's enough. So A big is complete. Is complete in soup metric. What do you need? I mean, to go through the review. If not, I'll go through some examples. So you can all understand what I'm talking about here, right? What is points-wise convergence? What is uniform convergence? What do I mean by this one's complete? In metric. Do we use this term? I forget. Sorry. 1 minute. Let me check. I think in your term, you use some like C, or you CP was B. CP was B. Forget it. Just something like this. So this one's complete. Yeah, instrument. So, anything? No? Oh. Then, examples. You have seen x to n, and something like nx, something like that. But I'm not going to work on those because like you should work on those by yourself, like maybe the day before the day. So let me go through some interesting examples about Taylor theorems. Right. So let's consider about sine x. I want to approximate sine x. How should I do that? We have learned it in calculus. So you know something like equals to x minus 3 on x. So it's third plus x to the fifth. You know this one, right? From your calculus course. Yes or no? I'm not so sure what you have learned before. Have you learned this kind of thing? Yes? Okay, I see some nodding. So, you can clearly see this is from Taylor. Right? So, f1 of x equals to x. F of 3x equals to x minus x. That's because, yeah, you just put sign here, you can see like 1, 0, minus 1, 0, 1, minus 1, 0. So you see something like 1, 0, minus 1, 0, 0, 1, 0, blah, 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 blah. So you see this kind of thing. And I want to prove that this equal is really equal. It really means equal. So maybe let's check it on some on R. Alright, I want to prove that. I want to show f2m minus 1x or fnx. You should see f2x equals to f1x, something like that. So you can write down something like fnx. So f2x equals to f1x. Also 4 equals to 3. Right. Sine x uniform. some bounded interval, negative nm. So given any interval like this, you know f and x converge uniformly to sine x. Why is that? Because sine x minus f and x by Taylor's theorem. What's the remainder? The remainder is this one. X to the n, f, and c. For some c between x and 0. Right? This one equals to what? That's or equal to n plus m, 1 over m, what's that called? N, or something like that. N to n, this one. This one converges to 0. So this one is uniformly bound by this. So how do you find? If I want you to like rigorous prove it by epsilon delta, you should write something like for every epsilon you can it should be for every epsilon you can find an n such that this one is smaller than epsilon, blah 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 blah. You should like go through various we have done it like several times. So you can see this. But sadly, the thing does not work so well generally. Let's consider another function. Example 1, example 2. Then we consider f of x equals to exponential minus square, to the minus x squared. So what is f prime of x? Do you know how to differentiate this kind of thing? I'm not so sure, but it should be negative 2x exponential this one. One over square over. Check. Let me check. 1 over square, 1 over x squared. It should be 1 over x squared, right? 1 over x squared. What do you think about it? It should be 1 over x squared, sorry. 1 over x squared, 1 over x squared, so that's this one is 0. So when it comes to 0, this one is it should be this one, sorry. So you know f0 is 0, f prime of x equals to so it should be negative 2 should be 2x over 1 exponential 1 minus x squared. Yep. So you know that because exponential is faster than this one. So you know f prime of 0 is equals to 0. And also f prime x equals to something like differentiate this thing, so you get negative 2x squared over 1 squared over 1 plus 2x over 1 4x squared over exponential 1 over x squared. And you see this one vanished to 0, this one vanished to 0. So f prime prime 0 equals to 0. And actually, no matter how many times you differentiate this, you can see that this one always exists in every term. So this term is always 0. It seems like the function here is a function so at this point it's too flat. It's so flat that any derivative, any order's derivative at this point is 0. But it changes. Right? Something like this. So actually, this property like sign does not always hold. It depends on your function. I will call this function like as analytic function. If its Taylor series exists and the Taylor series converges to the function itself, we call this kind of function an analytic function. But generally, we're dealing with function like this, right? It's just totally messed up. Okay, cool. I think that will be today. Just that will be fair. I'll tell you what question would be on your exam in the third period. Not exactly the questions, but the materials they covered. Cool? It will not be like too hard if you go through all the quizzes and practices. Seems like I need to stop it by myself.